Hi, everyone. Thank you for your time today. My name is Blake Ericson with Montrose Environmental Group. Here to talk to you today a little bit about some enhanced measurements, particularly of low concentration emissions from combustion and other non-combustion sources. We're primarily going to be talking about some of the involvements of some of the new technologies that we're currently utilizing and seeing out in the industry, and hopefully you'll find this presentation beneficial. So a little quick overview of what I'm going to be talking about today. We just want to briefly touch on traditional stack testing, where stack testing has always lied and where changes are currently being made. We'll dive into some of the advanced instrumentation that is currently being used, go over some data sets and some method comparisons, and finally wrap it up with a little summary. So the reality of traditional stack testing, if you've ever been to another presentation that I've done, I've used this image on a couple of instances, and I always like using it because it demonstrates really what stack testing is. This stack is give or take 120 foot in the air, if not a little bit more, a little bit less. And you can see that gentleman up on the stack pulling up that 5-gallon Home Depot bucket. It's been mentioned to me from colleagues before that we wish we had a GoPro or some camera set up to where we can see how many times that bucket is being lifted up and dropped back down on the ground to get all that equipment that you see on the screen. All the sampling equipment, sometimes meter boxes, pumps, rails, probes, whatever it may be. All this, it may only be 20 pounds or so on the ground, but when you involve wind and weather, this is a really tough job. Bob Finken has famously said, and one thing I've picked up from him, stack testing, you start at the top and you make your way down to the ground. And that's kind of the running joke. We've all been on top of these stacks, and to get really good data requires you to climb up high in all weather, no matter if it's inclement or not. Testing needs to be done at all times of the year. So just want to start off with saying thank you to our teams that are out there doing this. This is a tremendously difficult job, and we understand completely. So just so you know, if you're on the customer side of things, if you see stack testers sort of sitting around relaxing, this is a good thing. That means testing is going smoothly, nothing to be too concerned about. If you see some scrambling around, that's when you can start asking the project manager on site, hey, is everything all right? And usually things are a little bit of organized chaos, as we say. So lots of variables in traditional wet chemistry test methods, whether it's CTM, O27, CARG 430. These analytes are so important, and we'll get into that a little bit more. And the old adage is, if it's not broken, don't fix it. And I agree to some extent, but technology has come a long way. We don't want to stand still and just kind of watch things pass by and advance on. There truly are better ways to precisely and accurately collect really, really good data. One kind of crux with these wet chemistry methods is that they are very proven, but they are very technique driven. It takes a very skilled personnel, very skilled project management to really understand how to collect high quality samples, especially at a natural gas turbine or a startup project. Test runs typically are lengthy, to say the least. They can go upwards of 4+ hours to get you really low detection limits on your particulate matter or other analytes of interest. And furthermore, from there, most of the samples have to be shipped off-site to be analyzed in a laboratory. So, it's one of the downfalls. You're not going to know your numbers right away. They are very analyte specific, requires a lot of equipment to get all the numbers that you may need, a lot of personnel, and it is, once again, very technique driven. Why improve, the reliability of test results? Once again, going back, if it's not broken, why should we fix it, Blake? There's a lot of variability, in terms of wet chemistry test methods. We're looking at a tremendous amount of human error. If you're not good at what you're doing, the mistakes do happen, equipment fails. Everything has to go very well in order to do a really successful stack test. The results that you may get from some of these wet chemistry methods may not properly represent the actual emissions. And when I say this, you might get a detection limit. But what if your number is below that detection limit? And is that really a real number? How do you truly know that? That's some of the crux to some of the older methods is they're limited to what they can get down to. So the flip side of that is if your number is too high, you're going to run into the possibility of getting hit with NOVs, fines, a lot of public scrutiny. That's such a big thing nowadays for our customers. With the internet and social media being so prevalent, word spreads really quickly. So you want to make sure that your unit is really operating the way it's supposed to. You want to make sure your abatement systems are doing their jobs. That way you can take that defensible data and show, hey, look, we're doing everything we can to make sure our emissions are in check. On our end, if tests may fail or numbers are too high, whatever it may be, retesting may involve, that involves more people, another string of testing, more time, and time is money. You're waiting and the expenses will really pile up if more testing or additional testing needs to be done. Quantifying beyond just detection, why get lower than what the current detection limits are? I can't tell you, how many times this has turned out to be such a positive note for several clients, especially EPCs and turbine manufacturers. When you can take really low detection data and show, hey, our units are performing way better than anything that could be traditionally see it in the past, you can take that information and potentially help out with fines, with permitting down the road. In the end, it really just makes all of us look a lot better. We care because the landscape is changing. Every day it's so fast to keep up with all the changing technology. But if you don't adapt, you're going to be left behind very quickly. We care because not only of the cost benefits, but the performance benefits. It could really help, especially with your startup and shutdowns. The health information, once again, is so important to the public. The data, when you're at these really low levels, you're in the weeds. It is so important to be precise and accurate. You better make really darn sure that data is right. And technologies do exist nowadays that are extremely accurate and extremely precise. The advances is not only on the technology side, but on the reporting and the data quality side. It overall is just a better future for all of us in this industry. And to have true on-site analysis with real-time results would provide a tremendous advantage. Which leads me into the first technology FTIR that I'm going to be talking about today. This is the Starboost Technology. It's manufactured by a company called Max Analytical. They're based out of Connecticut. Great company, doing a tremendous amount of work to really drive these detection limits so low. Long story short, really accurate analyzer, real-time results. We can get readings from a couple of seconds, but most of the time when we're doing compliance, we're looking at about 1 minute averages. So these units are very useful for startup shutdown data, for process optimization, and a slew of other things, not just compliance testing. What is the difference? It's still US EPA method 320, ASTM 6348 compliant. It's a good method. We have lots of experience with it. The detection limits, particularly for formaldehyde and a handful of other compounds, ethylene oxide is similar. We're looking at about 8 to 10 parts per billion, excuse me. That's 10 to 20 times better, sometimes up to 50 better detection than some of the current FTIRs and some of the other technologies that currently exist. Once again, it's real time. There's no baseline drift. And there are some add-ons that can really, really drive these detection limits even lower than that 8 to 10 ppb that I have listed with 10% moisture. A little bit of data. This is actual startup shutdown data from a source. We'll have to keep that part confidential, but the main takeaway from this screen that I want to show you is that, you know, look at the variation of the emissions, you know, from cold starts to, you know, to the peak down. You know, they were moving this unit at all different intervals, different water injections, different fuel rates. Very, very interesting data set for the customer. But the Starboost handled it. Basically, the formaldehyde was in the weeds, you know, hanging around 30 parts per billion down to 10 parts per billion, and sometimes popped all the way up to several ppm, especially on the cold starts. So we tracked this data largely. It was well over a 12-hour day. You can kind of see the time slots down there, but they were able to go through several conditions over the course of one day. Looking at this data a little bit deeper here, this is the same data set from before, but we're just pulling up a little snapshot. This was about an hour average, which is what you would see for a typical compliance test. And we're looking at 17 parts per billion. That is a wet number for formaldehyde, and a 3 ppb standard deviation. To me, that's incredible. You know, I believe we derived the, you know, the detection for this instrument to be about 9 to 10 parts per billion, taking 3 sigma of the standard deviation there. And, you know, so the client was just so excited to see this data, and it really proved that, you know, there's quad Y and it wasn't lifted, but there are a lot of mumblings going around that it could happen any day. And that's that 91 parts per billion dry corrected to 15% oxygen. But what this data shows is that when they're burning natural gas, that 91 parts per billion is nothing to sweat. When this unit is running at full, you know, full utilization, high megawatts, it's running really, really clean. And it was really good to see this data. A little comparison set on a little bit of a different, you know, energy system, looking at some boilers. We wanted to use the Starboost to look at natural gas, but also to look at fuel blends. So there was 3 boilers in this case. And the main takeaway from this is, you know, look at how consistent each of the boilers are with the natural gas, looking at an average of about 30 parts per billion of formaldehyde. And then with the fuel blends differed and the loads differed, you know, so there wasn't as consistent of a study for us with the fuel blends. But what it does show is that the fuel blends have a tremendous amount of variability. You don't know what you're going to get. It's going to be different. Each unit is going to handle the combustion of that gas a little differently. But with natural gas being pushed so heavy, once again, really great to see these numbers. Now, I talk really positively about the Starboost, but it's not all perfect. Every instrument has its limitations. So the Starboost, one of the main issues, and it's not an issue, it's just what it is, it's very limited. It's essentially like taking a magnifying glass on a very specific region, and we can only see a handful of compounds. So in this case, with this FTIR, with the aldehyde filters and all the advancements in this instrument, we can really only see formaldehyde, methane, ethane, moisture, and maybe a handful of other compounds. Anything around that, you know, roughly 2,500 to 3,000 wave number in FTIR terms, we can see that region very well. Anything outside of that, we can't see it. And it's just because we're not looking there. So that's the main limitation with the Starboost. Not to call it a one-trick pony, but it's just really good at getting really low detection for very specific compounds, primarily formaldehyde, ethylene oxide, and there's a handful of other constituents that we're currently being asked to research right now. Current applications for the Starboost, like I previously mentioned, a lot of reputation behind this instrument. You know, this isn't something that we've done one project with and we're sharing with. This has been over the course of a couple of years now. We're looking at 60 plus individual projects ranging from process optimization to compliance testing. We have a tremendous amount of confidence in this instrument. We've challenged it time and time again. We can spike parts per billion levels into the sampling system, get really good recoveries back. So we've really challenged this instrumentation. We've even done method 301 validation with this instrumentation. And there's a whole slew of things that this instrument is particularly useful for. Those are all listed right here in front of you. And if I will mention too, if there is ever a HAP or VOC of focus for you that you really want to hone in on, let us know, and we can lead the research and development to make sure we really dial that one in. Another technology that's being used, and this will be used in our cross study later on, is called the MAX. And this is also developed by Max Analytical out in Connecticut. And this is a little different. This is a method 18 analyzer, and we use a GC in line with the FTIR. And we collect samples on a TDT tube, which is a thermal desorption tube. So sampling is a lot different than the standard FTIR. We're going to be pulling a slipstream into these carbon capture tubes, and we get about 10 to 30 parts per billion detection for formaldehyde with this MAX. The one beauty with the MAX is that it's also really nice for like BTEX compounds. Those detection limits will be roughly in the same wheelhouse as this formaldehyde, 10 to 50, let's just call it to be safe. So the applications for the MAX are a little bit different, but very important to what we do. Real quickly, sampling, as I said, is a little different. We have the sampler here, and in the sampler, there's two mass flow controllers. We're taking a very, very small slipstream over the course of the hour or whatever it may be to sample. We're pulling roughly 1.5 liters of sample through the tubes, and we are then taking the tubes and we're putting them into the desorber on the right of your screen, just below my picture here. And we're using nitrogen as a carrier gas. So the whole tube, the gas matrix, it goes into the GC column. It desorbs through the tube, goes into the GC column, and based off of molecular weight, time, in a typical GC analysis, goes into the gas cell, and then we do the analysis from there. So the GC separates each compound individually, like I said, based off molecular weight, and we're doing pretty similar analysis to the FTIR, but also a little different. This is a little example of actual formaldehyde sampling. This is actually one of our direct calibrations. Method 18 is very strict with its calibration requirements, so we have to do triplicate calibrations, so a low, mid, and high level. And in this case, this would be our mid-level calibration. We're aiming for about 1,000 nanograms. So once the tube is run, we then do the analysis, and with the little animation here, we can then take that, match where the background in the sample is, take a little snapshot of that window and get, okay, our average is 1,020 nanograms, whatever it may be. But we take a window of time to get that number and to get us an accurate number. The actual test run example, once again, not to spend too much time here, but this is an actual compliance test that was MAX was utilized. Very strict QA/QC per method 18. You can see with all the numbers, we had a nice spike recovery of about 87%. Accepted criteria is 70 to 130. So going back to the sampling, we take a spiked and an unspiked tube. We compare the two. That helps us get a recovery corrected sample and a stream recovery corrected sample. And in this case, on this turbine, we were getting about 38 parts per billion of formaldehyde. So once again, real low number. We were real excited to see it. Limitations. As I previously said, no instrument is perfect. This instrument is not real time. It's close, but we're going to have to collect the sample over the course of an hour, and then we have to do analysis. So each tube for formaldehyde is about 20 to 25 minutes. And if you're going to do BTEX or if you're going to do a slew of other compounds, that analysis time can get upwards of 50 to 60 minutes per tube. So a little bit longer of a test day, but you're still going to get really nice results. It is dependent on the analytes of interest. And I will say, if you put too many compounds in, it makes analysis extremely difficult. Too much moisture makes analysis extremely difficult. There are ways around this, but the MAX is not a perfect instrument. It takes a tremendous amount of knowledge and experience to really be good and effective with this instrument. A failed test, not a failed test, a failed spike, I should say, does require another retest. Formaldehyde has such a low boiling point that this can happen. Mistakes do happen. So we do recommend that the MAX is brought on site. As much as we would love to go out and send, test teams to collect tubes and ship them to a lab, we've just found that the hold times aren't all that exceptional, especially for formaldehyde. I mean, there's no easy button for this instrument. Little, proof of work. Once again, lots of applications here for the MAX. This is another one we didn't want to just throw it at you with doing one successful project. We've had over 50 to date. Lots of applications, primarily involving BTEX, formaldehyde, and a slew of other potentials in the works. We have seen hexane, toluene being requested at some natural gas turbine sites. Those are rare, but they do come up. But this instrument is very applicable to those testing needs. We also have a PTR TOFMS, and that is quite the mouthful because it is the proton transfer reaction time of flight mass spectrometer. And not to dive too deep into this, this is more of just an awareness. It's a fascinating tool that we have in a van, and we can drive this around. It's exceptional for fence line monitoring. There's a really cool data set that unfortunately was confidential and I couldn't share it. But essentially they took the data that they captured with this PTR, they overlaid it in Google Maps, and they kind of showed the little peaks and valleys of where they were seeing hits of ethylene oxide around the perimeter of a facility. So they took that map and they sent it to the client and said, hey, here's where we think your problems are. And it was tremendously useful for them to see visually where those potential issues were. Diving into method comparisons. So a little heads up here. Once again, we wanted to challenge these instruments. We didn't want to just take them out of the box and say, okay, we're ready to go. We wanted to do a lot of R&D on them, make sure that they were proven. These are tremendously expensive instruments, so we wanted to make sure they were really, really good at what they were promising us. So we took formaldehyde. Once again, that's the main course for this presentation. And you can see AP42 is the current emissions factor. And that just vastly overestimates, what is actually coming out of most of these sources, at least in my experience. I've done a lot of these turbines and boiler sets. I've never seen anything close to 240 parts per billion of formaldehyde. I'm sure it happens from time to time. But Carb 430 is a wet chemistry method. So at this site, we had, all these different testing methods to see where the formaldehyde was. You can see with Carb 430, highly effective method. It's very proven. It uses DNPH as a solution. Pretty nasty stuff, but it is prone to a lot of human error. And in this case, you can see the variation between the three test runs ranged from anywhere to 300 to 75 parts per billion of formaldehyde, and gave us an average of about 180. The advanced IR methods, which were the Starboost and the MAX, gave us about 45. And we also were seeing about a 10 ppb detection with these instruments. So it's safe to say that, you see a little bit of variation there per the runs, each run. I will say too that each of these runs were different conditions, but your variation is much smaller. Your standard deviation is much smaller, and our detection is just better. This is the actual data from the same testing as before, just in actual number form, so you can see it. Um, and you can see how close the Starboost and the Max, two separate methods, method 320, method 18, tremendously different. Each has different criteria, but we were really, really close. The biggest variance was that 4 ppb for our first test run. So we were thrilled to see this. You know, these are all three, I should say it again, different loads for each one of these. Um, so we were really testing these instruments to make sure that they were in the same wheelhouse. And it turns out they're pretty much spot on. So to wrap all this up and summarize it, once again, we have the technology available to really get low detection for formaldehyde, especially, and also ethylene oxide. There's a handful of other things that we are working on with the manufacturer, that being Max. Really, the possibilities are endless for these instruments and the testing methods. To me, the standard test methods, there's nothing wrong with them, but there's no true comfort. You're collecting your results. You're kind of leaving it up to chance to make sure your test teams know what they're doing. You send them off, and who knows, the laboratory results might be vastly different than what you expect. So the results just take too long. They're variable, and any sort of retesting is expensive. Having these advanced instrumentation pieces on site is so beneficial. Once again, they're not the perfect instruments, and they're not going to handle all of your testing, but for very particular needs, it's the way to go. You get the on-site analysis, really low detection limits, real-time analysis, and they're just powerful new tools. So this is the adaptation of STAC. This is where a lot of us believe the direction is heading, and the instrumentation once again exists. We can see things at a parts per billion level, and we have tons of data and tons of data programs that really bolster this information. So with that, I thank you for your time. I know it's not always easy to sit in these sort of Zoom meetings and listen to one guy talk for far too long. So please, if you do have any questions, please reach out to myself or Phil Copy. Phil is our in-house FTIR expert, and we can handle any question or request that you may have. Happy to do so. Once again, thank you for paying attention, and let me know if you need anything.